Welcome to our lecture series on lipids. Here we will learn about lipid storage and digestion in adipose tissue and the transportation of free fatty acids in the bloodstream. Adipose tissue, or body fat, or simply fat, is a loose connective tissue composed mostly of adipocytes. White fat cells, or monovascular cells, contain a large lipid droplet surrounded by a layer of cytoplasm. The nucleus is flattened and located on the periphery. The fat is stored in a semi-liquid state and is composed primarily of triacylglycerides and cholesterol esters. An average human adult has 30 billion fat cells with a weight of 30 pounds or 13.5 kilograms. If excess weight is gained as an adult, fat cells increase in size about fourfold before dividing and increasing the absolute number of fat cells present. White fat cells form the predominant form of fat in the adult body. Brown fat, also known as baby fat, is used to generate heat. Adults only have limited quantities of brown adipose tissue. Brown fat cells are plurivacuolar and have a considerable cytoplasm, with lipid droplets scattered throughout. The nucleus is round and is not in the periphery of the cell. The brown color comes from the large quantities of mitochondria. The energy available from stored fats is about 85% of the total energy available in the body. In adipose tissue, especially white fat cells, fatty acids are liberated and released in response to hormone stimulation. For example, the binding of epinephrine to adipose tissue behaves in a similar way to the activation of energy-releasing pathways in the liver. In adipose tissue, epinephrine binds with the G protein-coupled receptor that activates a downstream G protein. The activated G protein turns on adenylate cyclase, leading to the production of the second messenger, cyclic AMP. Cyclic AMP, in turn, binds with protein kinase A to activate many downstream target pathways. One target is triacylglyceride lipase. pKa mediates the phosphorylation of this enzyme, increasing its activity. This enzyme hydrolyzes one of the fatty acids from the triacylglyceride, yielding one free fatty acid and one diacylglyceride. Other constitutively active lipases cleave the other two remaining fatty acids from the glycerol backbone. Fatty acid binding proteins chaperone the free fatty acids within the cytoplasm. Proteins such as fatty acid transport protein, FATP, are used to excrete the free fatty acids into the bloodstream. Digestion of triacylglycerides, TAGs, also releases the glycerol backbone. Glycerol can be converted to glycerol 3-phosphate by a glycerol kinase enzyme. The glycerol 3-phosphate can then be oxidized to DHAP by either an L-glycerol 3-phosphate oxidase enzyme or glycerol 3-phosphate dehydrogenase enzyme. Here it can enter into the glycolytic or gluconeogenic pathways. When your body needs energy or needs building materials, fat cells release fatty acids into the blood. There they are picked up by serum albumin and delivered to distant parts of the body when they are utilized for energy. Serum albumin is the most plentiful protein in the blood plasma. Each protein molecule can carry 7 fatty acid molecules. They bind in deep crevices in the protein, burying their carbon-rich tails safely from the surrounding water. Serum albumin also binds to many other water-insoluble molecules. In particular, serum albumin binds to many drug molecules, such as ibuprofen, and can strongly affect the way they are delivered through the body. In the next section, we will examine how cells that receive these free fatty acids utilize them for energy production.